Now, in this question, they mentioned that the conductor and magnetic field are in the same plane. That means it's within like the paper, plane of the paper. To find the expression for force per unit length. Now, remember, in this case here, your magnetic field and your current are not perpendicular. So what you have to do is go to resolve either the field or the current so that they are perpendicular to each other. Because in this case, the one that's angle is the magnetic field. So if you resolve it to two components, the magnetic field will have two components like this. The horizontal component of the magnetic field will be parallel to the current, so it will not give you any force. But the magnetic field that's perpendicular to the current will give you the force. So the component will be B sine theta. So the formula of the force would be then BIL sine theta, because you're taking the vertical component of the magnetic field. But in this case, they want force per unit length, so you have to bring the length over. So it's just BI sine theta. So the answer here is BI sine theta. The next part is the direction of force on the conductor. So you use a Fleming's left hand rule. Alright, take the field as downwards along the plane of paper. Current is to your right, then you will get the force into the plane of paper. So the field is downwards, current is to your right, then your force will be into the plane of paper. A small rectangular coil ABCD contains 140 turns of wire. So I want you to imagine that this coil here, there are 140 turns. That means it's a one wire going around 140 times. And the sides are given, the lengths, and then they told you that the coil is held between the poles of the magnet, okay, which is here. And you want to actually find out for the coil in the position for maximum torque. State whether the plane of the coil is parallel to or normal to direction of the magnetic field. So what they're trying to say here is, I mean, all these values are given to you like current and torque, but that's not important for the first part. They're asking you which orientation should your coil be in order to produce maximum torque. Now, some people say, what is this direction considered as? Is it parallel or normal to the direction of magnetic fields? How do you see? Now, the plane of the coil is referring to this area enclosed by the coil. So I want you to imagine this is the coil, and the area inside is the plane of the coil. So can you see this area is horizontal area? So that's called the plane of the coil. Now, when it is parallel to the field, this is the orientation. Because how do I know? To help you imagine better, I will call this north and south. Of course, you can do the other way around. I'm just imagining, just an assumption. So the field will be this way, right? So if the area here is horizontal, it's considered to be parallel to the field. Now, if you're wondering how normal to the field will look like, you rotate this coil until it's like this. Can you see the area now is a vertical area enclosed by the coil, and the field is still the same. So can you see this area is 90 degrees to the field? So this is when the plane is normal to the field. So which orientation, this or this, will give you highest torque? So I'm going to explain to you once, then later on you can just remember which will give you the highest torque. Now, for example, I'm going to imagine the current goes from A to B to C and D and back to A. I'm assuming the current flows this way. Now, if you take the current here and the field here, that means you take, if you're using Fleming's left hand rule, you point your pointer finger to the right, current into the plane of paper, you will get the force downwards. Alright, you can try Fleming's left hand rule. And therefore, the force on CD should be upwards, because the only difference between AB and CD is that the current is in opposite directions. So the force on AB is downwards and CD surely upwards. If you don't believe, you can also use Fleming's left hand rule here. Okay, then we want to talk about the force on BC. Now, do you realize that BC, the current is to the right, the field is also to the right? So this is an example where the current is parallel to the field, so there's no force. Similarly, current in AD is parallel to field, also no force. So you'll notice that there are only two forces acting, one on AB and one on CD. Now, what happens when you rotate the coil? Now, if you can use Fleming's left hand rule again, you can test it out. You will notice that the force on AB will be downwards, the force on CD will be upwards, the force on BC will be out of the plane of paper, and the force on AD will be into the plane of paper. So even though you have 4 forces here, you will not get any torque. You know why? Because these two sides, right, AD and BC, right, one force is into the plane of paper, one is out of the plane of paper. So I want you to try taking your calculator or your phone and putting it in this orientation. If you push in from the outside and push out from the inside at the same time, you will not get any rotational effect, because the two forces would pass through the same point. There will be no perpendicular distance between them, so it won't rotate. Similarly, you take your calculator, put it in this orientation, you push from the top and push from the bottom, you will notice that it also will not rotate, because these two forces are going to intersect in the center, right, or intersect along this line. So there's no perpendicular distance between these two forces, therefore there's no rotational effect. So even though there are only 2 forces here though, remember that this is actually a couple where the 2 forces here are equal in magnitude but opposite in direction and separated by a distance. So this is a couple, and it does give you a turning effect. So in other words, the orientation that gives you the biggest torque is this, alright, not this. Right, so the answer here would be parallel. That's all. They didn't ask you to explain. This explanation is for you to understand. Right, the next part, they told you that if the coil is in this position, find the force on the side AB. Now you might be tempted to use the formula F equals to BIL, but unfortunately we do not have enough information. Now we don't have the magnetic field strength here, so we cannot use F equals to BIL. But what they did give us is the torque. And remember, the formula for torque is the product of one of the force and the perpendicular distance between the two forces. Alright, and now in case I'm wondering, are these two equal in magnitude? Definitely, because it's the same current here as in here. These two sides are the same current, same magnetic field strength, so therefore it's the same force. So you take the product of one of the force, F, which is what we want to find, times the perpendicular distance between the two forces, 2.8 centimeters. Don't forget to convert it to meter, and you will be able to get the F. For the next part, we are going to find the force on BC. Do you realize BC is parallel to the field? So the answer is just 0. And then the last part, use your answer to show the magnetic flux density between the poles is 70 milli-Tesla. So actually, you can use the force here, but not straight away. You know why? Because this force is on side AB, which I want you to understand is on actually 140 wires, because you went around 140 times. The same current goes around 140 times. So if you're talking about F equals to BIL, you need to remember that this force is strictly for the force on a single wire. So what we need to do is we need to take this force and divide by 140 to get the force on one single wire only. Then you write down the B, which is what you want to calculate. I is the current given in the question. Alright, and also L. Now this L must be careful. You must take the length of the wire in the field, which is 4.5 centimeters. Alright, and then you should be able to get your B in terms of Tesla, and then convert it to milli-Tesla. Now you want to define the Tesla. You must remember the definition of the flux density comes from this formula, F equals to BIL, which means to say the current and the field must be perpendicular. So the definition of Tesla or magnetic field strength comes from this equation. So normally if you define flux density, then it's just force per unit current, per unit length on a conductor placed perpendicular to the field. But if let's say doing the Tesla, that means you must say the force of 1 Newton, current of 1 ampere, length of 1 meter in the field, perpendicular to the field. So this is the definition. 1 Tesla is the flux density if a wire of length 1 meter carrying a current of 1 ampere, force exerted 1 Newton, right angles to both the flux and the current.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with 1 or 2 past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.